Okay, so today we are happy to have Amanda Hirschi telling us about Lagrangian theory.
Thank you very much for the invitation. So I'm going to talk about joint work in progress with Kai Hugtenburg. I mean, it's very close to being finished. And I will first start with some background. And so I guess idea behind open Gromov-Witten theory is that the usual Gromov-Witten invariants are very strong invariants in symplectic geometry and give us lots of results. And since many of the classical results, such as Gromov compactness, also hold for curves with boundary on a Lagrangian, one could hope to define invariance similarly by counting maps from surfaces with curves with boundary, where the boundary is mapped to a Lagrangian. Now, the sentence may be slightly controversial, but so defining invariance based on count of closed dots on closed holomorphic curves is reasonably straightforward on the one big assumption, namely that you have a robust virtual framework or virtual counting framework. Or sufficiently restrictive assumptions on your target manifold. Now, doing the same in the open setting, so if you no longer look at closed curves, but curves with boundary on a Lagrangian, there are two problems which arise. So doing the same in the open setting, runs into see this runs into two more additional problems. The first one is that the moduli spaces we consider are not necessarily orientable. So one has to impose Lagrangians, one has to impose conditions on Lagrangian so that the index bundle of these moduli spaces actually is orientable. I will say more about this in a moment. And the second problem is that these moduli spaces also have boundary. So when I say boundary, I also mean they can have corners, such as boundary constraints. So I just need to pull this up strongly enough. So the first problem has been completely determined by Penka-Georgieva. We essentially determined the first Stiefel-Whitney classes of the Cauchy operators of these real Cauchy operators. And also by Jake Solomon. So one can even ask for kind of the Lagrangian to admit a pin minus or pin plus structure or a relative spin structure. One option, which is the one we use in this talk, is to consider relatively spin Lagrangians. Which I mean that, first of all, the Lagrangian is orientable. And second condition is that the second Stiefel-Widner class of the tangent bundle lies in the image restriction map. So X is my, should I continue this notation? X is my symplectic manifold, and then will be kind of my standard Lagrangian. And what this essentially means is that we can find a vector bundle on X such that when you restrict it to L, the direct sum such that this direct sum as well is spin. And a relative spin structure on L is simply kind of a choice of such bundle and a choice of spin structure on the direct sum. So kind of, yeah, let me just say. On the Lagrangians in this talk, will be embedded and carry also a relative spin structure. I mean, many of the kind of more geometric results I will state later do not require kind of that L carries a relative spin structure, that as soon as we start defining kind of like doing algebra, this is necessary. Simply because we need some sort of orientation if you want to define invariance. Okay, so this problem essentially deals with like kind of imposing these assumptions, which are obviously not always given. So just take, for example, Rp2n. This will not be orientable. So in particular, cannot be relatively spin. But once you have these assumptions, orientability is kind of fine. Although, of course, one needs to kind of be careful when computing orientation signs. And then the second problem is, or like the second kind of issue with the fact that we have boundary means that we cannot define a fundamental class or virtual fundamental class, depending on the setting, because yeah, they just don't have one. Yeah, so and so since it does not exist a virtual fundamental class, one has to somehow work around this. So there's several kind of options to do this. Kind of one option is, which is, for example, what was done by Georgieva and Singer in the case of real Gromov-Witten theory, is to kind of glue moduli. If you have two moduli spaces with the same kind of boundary or certain same boundary strata, you glue them together along the boundary strata to actually obtain a moduli space without boundary, on which you then have a fundamental class. So let me say this somewhat vaguely. Yeah. Boundary structure. Where one, of course, has to be very careful about kind of how orientations change, so that the kind of finite moduli space is still orientable. Just see. Or one kind of actually says, well, the boundary strata have in some sense meaningful algebraic information, and we just have to work on a chain level and somehow use the fact that the boundary is actually kind of very nice, very recursive in a sense. I will make more precise later. Yeah, I will kind of follow the framework of Solomon-Tukachinsky, and we will work on the chain level. Let's take one. So let me just say a bit of history on invariance. So for a long time, kind of the moduli spaces I will also write down in a moment are somehow considered not sufficiently nice to actually extract invariance from them. And kind of the first work, but this was by Jean-Yves Welchinger in dimension 4 and 6. And if I kind of remember correctly, in the presence of kind of when the Lagrangian is fixed, it's the fixed point locus of some kind of anti-symplectic involution, in which case somehow one can kind of certain disk bubbles come in pairs with opposite signs, and so they cancel, and one can obtain invariance if one is careful enough. Then there's work by Kai, who defines such invariance for Lagrangian mass of index 0. In Calabi or Prefo. Leo defined invariance, should also say, okay, both of these invariants here in genus 0. Leo defined invariance in all kind of in all genera, but in the presence of an S1 action. So we have some Hamiltonian S1 actions on X, which preserves a pointwise, not setwise. There's also work by Diaghieva, and I'm writing Zinke in brackets because their work together is more kind of on real Gromov-Witten invariants, which are related but not quite the same as open Gromov-Witten invariants. And she defines them if L is in this real setting, so if L is fixed by an anti-symplectic involution. And then the work which is most relevant, what kind of I'm going to talk about, is the work by Solomon-Tukachinsky. which essentially said we are going to ignore all the transversality issues and just assuming our moduli spaces are kind of regular. So in particular, smooth orbitals with corners and the evaluation maps are submersions. So, and then they just kind of developed an algebraic framework to extract invariants from the moduli. With the idea being, of course, that somehow once you have a kind of a good virtual framework, you should somehow quite easily generalize whatever they are doing kind of to the general setting, and this is exactly what we are going to do. And then there's also kind of work by Ekman and Schindler on scheme valued. Without the interface. Yeah. Any questions?
Last one is in dimension 6.
Yeah. So that's also, yeah, this is also in low dimension. Okay. So yeah. Let me now be a bit more specific about what moduli spaces I'm actually considering, and kind of what kind of structure do they have. So kind of not very surprisingly, we call them moduli spaces of open stable maps, or sometimes also bordered stable maps. So let me start. I'm fixing some almost complex structure tamed. So maybe say, sorry. So we have some closed symplectic manifold. And some embedded Lagrangian inside X with a relative spec structure. And we're fixing some J, which is tamed by omega. And we're fixing some homology class in relative homology. And now kind of these moduli spaces come with even more subscripts than the moduli spaces of kind of ordinary stable maps. So now we have namely the genus of our curves, and we have H is the number of boundary components. And then we also kind of distinguish between interior mark points and boundary mark points. So yes, I mean, probably know what they are. Now we have smooth maps from some Riemann surface with boundary, where the surface might possibly be nodal, and I allow kind of interior nodes and boundary nodes. And kind of with the usual conditions that, of course, this map is supposed to be J-homomorphic, and should represent the cloud theta, and also kind of the automorphism group of the whole thing. I should say we have some interior mark points, okay, in here, and some boundary mark points in here. Sorry, getting messy. So we want this whole thing here to be finite. And then we quotient as usual by refactorizations of the domain. So yeah, this is our moduli space, which is kind of, in a sense, the obvious generalization of the one in the closed case. So you said one could kind of work on the sideboards or additional things. So let me draw my pictures here. So why do these moduli spaces have boundary when those in the closed case don't? And they kind of keep, I mean, when I say boundary, I mean, of course, always in the kind of virtual sense. The key point is that at interior nodes, you have kind of 2 degrees of freedom. You can somehow twist or increase the cylinder, and at boundary nodes, you only have 1 degree of freedom. So boundary nodes kind of give you the boundary strata. So if you, for example, start with a curve like this, maybe it's just here mark points and boundary mark points. So this is an element of, we have genus 1, boundary components 1, 2. And there are several things that can happen. So boundary nodes also come in kind of several different types. So for example, if you have no mark points on the boundary can just collapse. And you have something like this. You should, I mean, yeah, maybe I've done this a bit. So you should really think of this as somehow becoming something like an interior mark point in the surface, but you think of it as a boundary node. And these are kind of called boundary nodes of type E. So also the local modulus for these is elliptic. Then you have kind of the classical disk bubbling. Would, for example, happen in this case if the 2 mark points collide, if this develops. You could also have somehow that the geodesic here shrinks to 0, so you get something like Poynting surface like this. So no genus anymore inside. And finally, this is called an H2 boundary node. And you also have an H1 boundary node where somehow, if you have, for example, the curve here shrinks to 0. So you get something which looks like this. Anyway. So you see already that somehow the structure of these moduli spaces is somewhat more complicated than in the closed case, where if all the nodes have the same type and where all the nodes are somehow in codimension 2, or like all the nodal strata. And okay, I should also say here, since it's easy to explain with pictures, as you kind of see, any of these curves is obtained from kind of clutching another, in this case, smooth surface curve at kind of 2 mark points. Does that make sense? Okay. So for example, this comes from to have some surface like this. We have so a pair of surfaces. Then here with 1 mark point, and it is with 3 mark points. And you obtain the surface simply by gluing these 2 mark points together. And a similar thing happens here and here as well, although the situation is slightly less easy to see. Does that make sense? I mean, this property is kind of very important for getting invariance.
Not for the boundary collapse.
But boundary collapse might have that too. It's the image of where you just it's slightly, I mean, yeah, this kind of type of node is slightly weird. You should think of it as somehow saying an unstable disk bubbles off, and then you collapse it to a point. And it's this kind of surface is the image of that surface like this, where this node just is an interior mark point. And as soon as you have kind of, I mean, the structure for the moduli space of stable maps is the same, except of course that you require your map from such a surface to X to have kind of, you need to have some matching here. And in this case, you need that this map point gets sent to the Lagrangian. Does that make sense? Not quite.
But say when in the situation where you have that unstable disk, so you could presumably keep track of a matching marker at the node, yeah?
Yes.
So then you would have a little bit more data. But that doesn't help you. Or...
We didn't really manage to make it help us. I mean, what is kind of just, in some sense, I mean, yeah, this is like, these kinds of things are in some sense a major problem for invariance, and following Solomon-Tukachinsky, one kind of circumvents that by also incorporating into the kind of open definition of open Gromov-Witten invariants, and also incorporates counts of actual closed pseudo-holomorphic curves.
The same value accomplishment that did they assume this moduli spaces are regular also, or they?
No, I don't think so. So what Solomon-Tukachinsky did is that they kind of really said, well, we really kind of just want to see what is the algebraic structure given by these moduli spaces, and how do we kind of get numbers out of that. And so, yeah, they just didn't want to deal with the transversality issues, which, I mean, yeah. But they also build it in such a way that as soon as you kind of construct the necessary input for their construction, you kind of just run the arguments sufficiently formal that, yeah, one doesn't have to do any more work. Okay, so as you might also imagine, these moduli spaces are generalization of the usual moduli spaces of stable maps. So one has also kind of the same transversality issues in general. And let me just abbreviate also the name of my collaborator because it's somewhat long. Our first result is that these moduli spaces admit global Kuranishi charts. So and now in contrast to the closed case, this global Kuranishi chart has boundary respectively partners. So the second result deals with somehow the orientation issue. It says so in the situation we're on. So if L is equipped with relative spin structures, the global Kuranishi chart is orientable. It is orientable, it's also particularly canonically oriented. And finally, the last point, which is somewhat important for kind of also defining invariance later on, is that we can arrange for the evaluation maps at interior and boundary mark points. So call them I. Fine. So yeah, I should say here maybe. I mean, if you want me to, I can also define this, but a global Kuranishi chart always consists then of some manifold with a low, almost free G action, some vector bundle over this to which the G action lifts, and some section, equivariant section of this vector bundle, such that kind of the zero locus of the section, once you quotient by G, is isomorphic to our moduli space. And we can arrange for our evaluation maps from on the thickening. So they, first of all, they extend to the thickening, and second, we can arrange for them to be submersions. So we have interior mark points and we have evaluation at boundary mark points. And we can also arrange for them to be joint submersions. Okay. Should I say more about global Kuranishi chart, or is everyone reasonably happy with this?
Are you going to say what it means it to be charted with boundary?
Yes. So in the closed case, this is just a manifold, and now it's a manifold with boundary.
But I mean, does the boundary itself have its Kuranishi chart and there's some compatibility?
That is going to be my next theorem, yes. It does. Okay, so the first remark is that construction is a generalization to construction by of Smith, respectively, my work with Mohan Saminakhan. And it is literally not much harder in the open setting than in a closed setting. One just has to be kind of careful with orientations. So yeah, one certain properties, and that one has to kind of work a bit. And also, so we prove actually something slightly more general than what I've written here, namely what we're proving to any global Kuranishi chart, you can associate an orientation line. And this orientation line is kind of canonically isomorphic to the orientation line of the index bundle of this moduli space. And this is independent of kind of auxiliary choices you need to make when you construct this global Kuranishi chart. However, the third property is very much not independent of these choices. So, as in a closed setting, the construction requires the choice of auxiliary data. And so the third property let me requires certain properties of this data. But also, as in the closed setting, we show that if you choose different auxiliary data, your resulting global Kuranishi charts are equivalent. So kind of you can relate them by certain natural moves.
Can you say something about why you want it to be surjective from the thickening, not just some tangential conditional?
Oh, I've not finished my statement. Thank you. Sorry, say it again. I wanted to be subjective on the thickening.
Yeah.
These maps here?
Yeah.
I mean, I don't actually need them to be subjective, I just need them to be submersions. But this is not answering a question.
Why don't you require it only along zero section or something?
I mean,
maybe.
yeah, you're right. So all of, I mean, kind of one of, maybe this here. So, if you have some global Kuranishi chart for some spaces, and U is the G-invariant neighborhood of the thickening of the zero locus, sorry, of our section. Then just kind of restricting all of our data to U gives you an equivalent Kuranishi chart. So essentially it just means this representation of your moduli space, or this presentation of your moduli space, is exactly as good as this presentation. You only care about what happens close to zero section, and some all my statements I'm kind of implicitly assuming that I can just change by kind of restricting to some neighborhood of the zero section. Does that? I mean, there's one point which I will soon talk about that one actually needs to be very careful about this. But also it doesn't matter. And yeah, so the second statement is exactly what you asked before. So kind of the recursive structure of the boundary. Also holds on the level of global Kuranishi charts. So what I mean by this is that we can, as kind of this picture shows, we can write, pretending it shows, we can write the boundary strata of our moduli space as kind of fiber products of our moduli spaces. And we're proving in the statement here that this kind of the same is true, like if you restrict the global Kuranishi chart to the boundary stratum, so you just restrict to kind of the relevant boundary stratum of the thickening, then that resulting global Kuranishi chart is equivalent to a global, like to a fiber product of global Kuranishi charts for open-moduli spaces. Should I write this down, or is this kind of sufficiently? I think okay. People seem to be happy enough. Yes, and then let me see this here.
So when you say chart is boundary is corners.
Yes, so I mean, yeah, for me, boundary means it can have arbitrarily many corners. Yeah, sorry, yeah. Okay. So both theorem 1 and theorem 2 also hold for embedded Lagrangian cobordisms. So I should have defined this first, but a Lagrangian cobordism as little is a submanifold. It's a Lagrangian submanifold. Of X times C. We use the standard complex vector on C, such that for are sufficiently large. Intersection of L with kind of just some kind of half plane sufficiently shifted is isomorphic, diffeomorphic to some Lagrangian plus in X times that part of the real line, and similarly for the negative side. Sorry. So maybe picture here would also help. Essentially have it, so here you have to be aligned. And you have something like this. Maybe with, so it can have several ends. And here you just have something in the middle. But somehow the region where it's not just some possibly disjoint union of Lagrangians and X times how to be aligned, this region where it's kind of complicated has to be contained in a kind of compact subset. And once you have this, your moduli spaces, so yeah, the moduli spaces which were defined here, you can still define moduli spaces over an open stable massive boundary on such Lagrangians, and they will still be compact, respectively. And then we can carry out this kind of the same constructions as before, and we get this result here. So this result is important to actually get somehow certain relations between the algebraic operations I'm going to define in a moment, and for kind of a given fixed Lagrangian. And this statement will help us somehow interpolate between, say some things about how Lagrangians which are related by such a Lagrangian cobordism, how their invariants kind of are related. Okay. Sorry. So somehow we now have the geometric framework to start thinking about what we can get from this. And as discussed before, the fact that our moduli spaces have boundary respectively corners means that we can't work on homology, but we have to work on a chain level. So we now focus on disks. So open Gromov-Witten invariants have not yet been defined in high genus, essentially as you can see from this picture, because the boundary is just quite complicated. So yeah, we focus on this in this section, and by theorem 1, we can define operations. So like, using the following correspondences. So we have, I will immediately write out my thickening now. I will index it by the homology class. So, and the number of interior and boundary mark points. And one boundary mark point will be kind of special and just carry like the label 0. And we will think of this as the outgoing mark point. So we have a map to L here. And on the other hand, we have incoming mark points in the interior and on the boundary. And so we have kind of our evaluation map here, which is somehow the product of evaluation at interior and boundary mark points. What we can do is so we can define maps which following Solomon-Tukachinsky by Q on the space of differential forms on x to the power of k and l to the power of small l to the differential forms on l, namely by taking some homology class U, pulling it back along this evaluation map and pushing forward along the evaluation map at kind of this special outgoing boundary mark point. And since I'm working on the thickening, I can't just use the evaluation maps here because the thickening might have kind of an arbitrarily high dimension, which has nothing to do with somehow the virtual dimension for moduli space. So I do the same thing as what we do when we define a virtual fundamental class, namely we correct by kind of by multiplying with the Tom class of the obstruction module pulled back along the obstruction section. So this is now not the Tom class itself, but a representative of the Tom class of the obstruction module. I should also say now that kind of also to be able to better kind of fit in with the framework of Solomon-Tukachinsky, I'm now not thinking of T as a manifold, but I'm actually thinking of it as kind of the quotient. So before we had T and the full version, and I'm now thinking of it as the kind of orbifold quotient. So yeah, this is why you will not see G appearing anymore here. Is this fine so far? Everyone believes you can define these operations?
So have like some consistent choices of thumb classes along strata.
I mean, yes, this is kind of where a lot of difficulties appear. So yes, let me say more about this in a moment. Let me also say here that so you can kind of work. You don't have we chose the kind of the chain complex of differential forms since this chain complex has well-defined push-forward maps for submersions. You could also work with overmodes, but we didn't manage to. So we first tried singular cochains, and that was very unpleasant. And at some point we just used differential forms. But it would be nice if one could find somehow a rational chain complex, which gives you also singular cohomology, but where you also have these push-forward maps. But we just didn't find a suitable model, so we're working with this. So replacing, right. So as if we have real coefficients, and then we kind of replace the coefficients by another cofine. We kind of define an operation only depending on the number of interior and boundary mark points. By simply summing over, with the classical thing, by simply summing over beta. And one result is going in the direction of what you asked, is that so maybe let me also index this. So once you kind of choose your Tom forms suitably, the collection of these operations where you have zero interior mark points, forms the curved, or define the curved A infinity algebra structure. The cohomology ring of L with no Wyckoff coefficients. So yes, the way we do, I mean, in some sense, this is quite subtle. And we can also only find so the construction of these Tom forms, of compatible Tom forms, is inductively, and we can only do it for finitely many, finitely many thickenings at once. What we then use is a trick by Fukaya, using exactly kind of this result here of Lagrangian cobordisms to get a pseudo isotopy, which then kind of lets us in the end obtain an actual curved infinity algebra. So we kind of can only do it for finitely many mark points and find kind of bounded energy. Somehow we can always increase it because, yeah, that's kind of the idea behind this. And this is also the point here where one has to be careful about kind of what thickening one actually uses, and one cannot just kind of restrict to a smaller neighborhood, because you need these Thom forms here to be to have compact support. Because otherwise, yeah, like if you use a smaller thickening, then somehow the operations might not be the same anymore, and you lose this compatibility. Okay. So what I mean by curved A-infinity algebra is that the Q00 operation is not necessarily zero. And this is kind of messy, but so let's just assume for the moment that it is zero. If it is not, one has to use a gadget called a bounding chain or bounding cochain to kind of at least get that this term becomes, do some kind of bulk deformation so that this term becomes nice. But I don't think it adds the understanding if I write down some long formula now. So we need two more operations to define finally our invariants. So first of all, we can also define the operation Q minus one, which essentially means we actually have no mark point, no kind of outgoing mark point. We just have interior mark points. And this is just a map which goes to R and which takes the homological class and integrates it over the thickening. So we still look at disks, but there are just no mark points on the disk. And here we have to wedge again with kind of some representative of the Thom class of the abstraction bundle. And then the operation we have, is the one where we just consider curves without boundary, where I just write an empty set here. Yeah, I also read that somehow how we use exactly the superscript is a bit confusing, because now this map goes to X, where we do this, where we use kind of the same thing here, except that somehow we declare one of the interior mark points to be the outgoing mark point. Yeah, do the same thing. So yeah, one key problem to obtaining invariance is the following phenomena. Namely, we could have just one account kind of disks with boundary on our Lagrangian. What could happen is, since you have no mark points on the boundary, we could have one of the boundary stratas is the case where this boundary collapses to a point, and where this point still sits on the Lagrangian, but then somehow this sphere can just float off our Lagrangian, and somehow we don't see these disks anymore. And Solomon-Tukachinsky, used some kind of closed curves to kind of compensate for this. So yeah, it requires a bit more algebra. It was defined a certain cone complex where we take this class I, this map I, which simply introduces a commonly class over the Lagrangian. And then what? So I mean, it's kind of essentially the argument is the same as in Solomon-Tukachinsky. The class CL, where you now use the operation Q0 empty set and Q0 minus 1, so this would be converse sign. So this defines an element of the cone of this map. And we show that this element is actually a cipher. So now you need an additional piece of data, so which is a splitting of the map from the of the cone to the copoinal of I. We can define the relative potential. To be the image of this class CL under the splitting. So the splitting is but it has some geometric meaning if L is non-homologous in the symplectic manifold. So if L is homologous in X. Then kind of any choice of chain whose boundary is L defines such a splitting. Essentially, just take a class in here and you integrate it over B. Okay. Yes. Now the open Gromov-Witten invariants are the kind of coefficients of this relative potential. So this is a very non-satisfying conclusion to my talk, and I apologize. But in some sense, what I think it shows that, at least for me, what the actual, I mean, for me, just the kind of more actually somehow relevant algebraic structures associated with such Lagrangians are these Q operations, because you kind of can define them without having to use more choices. And also you can define them in high genus. But yeah.
So what do you say is the more relevant?
I mean, for me, it's just like, I mean, okay, personally also, I think not really an enumerative geometry, because I don't care as much about numbers, but I think, so in my opinion, actually these Q operations are somehow the actual kind of algebraic reflection of the moduli spaces. And yeah, somehow you then do some algebra to actually then get numbers in the end. And I mean, this seems like a very non-concrete definition, but Solomon-Tukachinsky actually showed that one can compute these things. They define kind of certain recursion formulas, so one can work with that. But kind of, for me, the Q operations are actually the more natural thing to consider and to look at kind of what structure do these things have. So I'm running out of time, so I will just say that our result in Lagrangian cobordisms actually tells you that somehow given given that some bounding cochains extend over your Lagrangian cobordism and so on, your open Gromov-Witten invariants are kind of actually invariant under certain natural operations such as Hamiltonian isotopy or change of J, which is something Solomon-Tukachinsky couldn't quite show, only in certain cases. And what we also kind of currently are working on is definition of these Q operations in high genus. So I wrote down the existence of the global Kuranishi charts and kind of these the equivalences between the global Kuranishi chart restricted to boundary strata and fiber products of kind of other global Kuranishi charts. These results all hold in high genus, and someone can define these Q operations also in high genus. And the structure they should give you is somehow a variant of the open-closed topological and formal field theory of Costello. So the hope is that kind of in the end they will give us, they should give us the same structure that was Costello defined, modulo some kind of things one has to do, and hopefully also give us a way to show that the categorical enumerative invariants he gets are the same as the actual Gromov-Witten invariants when one starts with somehow the A-infinity algebra defined using these stable maps. Okay, that was a lot of words. I thank you for your attention.
Say this Q map, so this would be basically evaluations of the moduli space at the points.
Yeah. I mean, in high genus one.
So that is before, so just before you really pack it into this A-infinity.
Exactly.
Yeah, so I think that's closer to geometry if you want to.
I mean, for me, it's closer to geometry, yes. And I mean, but it's also at the same time something which is much studied by algebraic topologists. So they have also kind of ways of extracting invariance out of this directly. I mean, I think it's still very, very good. Their work is great, and it's very cool to get invariance out of this. But yeah.
Yeah, so Wanda, is it possible to get some obstructions for what kind of topological properties Lagrangian has to have given the symplectic? So we give you a symplectic manifold, and then maybe not everything is possible as a Lagrangian inside.
Yeah, we're not quite there yet to be able to investigate that, but that would of course be interesting to see. Yeah. I mean, the hope is also everything we've done so far is somehow we have curls with boundary on a single Lagrangian, and which is embedded, but of course one could try to see what one could do for immersed Lagrangians, and